how do you get the simplicity of those, but still closely capture the real fluid motion? Okay. Luckily, someone from 1904, Ludwig Prandtl, has postulated something. You know, postulate doesn't has any fundamental reason. You just postulate. You know, postulate. I postulate, half of you will fail. If I postulate, mean it is not true. It can be true, it can be not true. Because postulate, just postulate, like your hypothesis. He said, he postulated that the viscous region will only occur in the region near the wall, whereas outside those walls, you can treat the flow as an inviscid flow. This one solved a lot of problems because of this. You can have your airplane. Okay, this airplane, the flow using this boundary layer approximation. Okay, so when you have a flow, the viscous effect will occur only in this region, whereas on this region, your flow will be equal with the incoming flow, or this potential flow. And it's proven to be very useful for us later. Okay, so this one was postulated by Prandtl on 1904, and it was later proved by his student. Okay, so I can postulate something now. I hope one of you will prove it. Okay, so this boundary layer equation bridges the gap between the inviscid flow, which is very simple to formulate, with the Navier-Stokes equation, which is very accurate. Okay, we highlight the good thing about both. Okay, because if you highlight the bad thing, it will be we combine the not so accurate result of the inviscid flow together with the complexity of Navier-Stokes. You don't like it, right? So you want to combine the good thing. The good thing is the simplicity of the Euler equation with the accuracy of Navier-Stokes equation. Okay? So that's all about the boundary layer concept. Now, let's take a look at some characteristic or the characteristic of boundary layer. Okay. Imagine this one is your plate. Be nice to me. Okay? I think I will take this one. The flow is coming from here. You know why I take the height one? Because the wall effect will occur only on this region, right? Over this region, this flow can be considered as inviscid flow. Okay, this inviscid flow is moving. This is the incoming flow that I have. It relatively has a flat profile, which means the flow is not disturbed by the floor. Okay, it moves together happily, talk to each other, right? Then when it touch this wall, what will happen is this fellow got attracted with the wall. It will stop. When it got attracted, it will not stay by himself. We pull up the next one. So the next one will slow down. Okay? And this one do not want to be alone, accompany him, so he attract the next one. Next. So it will slow down, but with higher velocity, far away from those, right? This fellow do not know what happened to that. So he keep moving as before. Okay? So this one is not your gangland, it's moving. Right? That's why you got this profile. Okay? Touching the wall, the velocity becomes 0. A little bit on top of it, the velocity is not zero, but it is not as big as before. So it's still moving at low speed. On top, getting higher, higher velocity and higher velocity, until the level of reach, your u will be 0.99 of the initial velocity. Okay? The location where you get 0.99 or 99% of u, this is called the edge of the boundary layer. So when Prandtl postulated, he didn't know how thick it is, he just postulated, okay? So in the region close to the wall will be viscous. The viscous force will be affected, will be significant. Then, how thick? Then he said, okay, as long as you find that the velocity on that region has 99% of the incoming velocity, then that is your boundary layer. At that time, you can say that. It's just like that. So that's the postulate. Okay? So here what we have known is this one is inviscid region, viscous region, incoming flow, and the edge of boundary layer is the characteristic is given by this. Okay, so this one is the real flow visualization photograph. From the flow, you can see that the flow in here, it is zero. Then it goes along, getting higher, and then afterward it will become flat. Okay, so this one is the real measurement. Okay,